Good afternoon, everyone. Thank you for joining us for our webinar series, Tech Talk. Today, we're excited to bring you XRD and XRF, complementary X-ray techniques for analysis of ceramic materials. I'm Melissa Goris, and I'll be your moderator this afternoon. Today's webinar is being recorded, so once it concludes, we will share the full video with everyone who's registered, and it will be posted to our website. All participants are muted right now. So if you'd like to ask a question, please feel free to submit your question in the Q&A below. We will be reviewing these after the presentation today. If you experience technical difficulties during the event, you can also add this to the Q&A panel so we can try to address it right away. Without further ado, I'd like to introduce you to today's featured speakers. Dave Vanderweel, Director of Technology Development at NSL Analytical, and Akhilesh Tripathi, XRD Applications Manager with Rigaku America, who will be leading us through our webinar today. Welcome, gentlemen. Thank you for joining us.
Thanks, Melissa. Thanks, everybody, for joining us for another Tech Talk here at NSL. I'm going to start out today talking about some ceramics in general, and then getting into XRF, and Akhilesh will then take over and talk about XRD. But first, a quick introduction to NSL, in case anyone out there is not familiar with us. So we're a series of independent testing laboratories based in the Cleveland area. We work in a wide variety of markets and applications for mission-critical uses, such as aerospace, energy, oil, and gas. I'm speaking to you today from our metallurgical lab here in Cleveland, and normally I'm just a couple miles away at our analytical lab, where we do things like chemical analysis, thermal, physical testing, and particle characterization.
Thank you, Melissa and Dave. So I welcome everybody this afternoon for this NSL Analytical talk organized on the scientific subject of XRD and XRF. So just like Dave, Rigaku is also an analytical company, just like the way Dave mentioned. We are located here in the Woodlands near Houston, Texas. Our headquarters are in Tokyo, Japan. Rigaku provides full services, instrumentations for anything related to X-ray, if I could put it. Our core strengths are micro area, micro volume, ultra thin films, high resolution, sensitivity and throughput, complex information systems, in situ, and automation. So these would reflect in the instruments provided by us on X-ray diffraction, XRD, which would be the focus of my talk today, where I will focus on crystal structure and lattice constant, X-ray reflectometry, small angle X-ray scattering, SAX in short, XRR for X-ray reflectometry, X-ray fluorescence, XRF, X-ray transmission, XRT, and X-ray computed tomography, XCT, thermal analysis, TA, and evolved gas analysis, Raman. These are other instrumentation that are sold at Rigaku. Our main products, and I would encourage all of you to go to our website and see many more and in much detail in the XRD are listed here. MiniFlex Smart Lab series, especially in the XRD, where I'm focusing today. Our XRF equipments, material element identification, quantitative estimation, chemical bond analysis. Those several line of XRF equipments are available today. And in the same way, TA, Raman, XCT, and non-destructive testing equipments are available.
Okay, thanks, Akhilesh. I'll start now looking at technical ceramic materials, just so we're all on the same page and speaking the same language here. So ceramics are, of course, inorganic materials. Typically, they're compounds of metallics or semi-metallic elements, such as shown there. Silicon, boron would be metalloids or semi-metallics, and of course, all the metals. Most often, we're talking about oxides, carbides, or nitrides, although there are other types of ceramics, such as borides and silicides. Some common examples of ceramic materials. So the oxides, alumina and silica, are probably two of the most well-known, used in a wide variety of applications. And we'll talk about the different types of alumina and silica later, and some examples of how those are analyzed for. And then titanium and zirconium are also very common oxide materials. But then also remember, we don't just talk about pure oxides, but mixed oxides such as zircon, which is zirconium silicates, different types of spinel aluminates, such as magnesium aluminate, and then a wide variety of other mixed oxide materials all fall under the ceramic category. Carbides are another very common form of ceramic material. Everybody's heard of silicon and tungsten carbide probably for cutting tools and bits. Boron carbide and titanium carbide and zirconium carbide are also used to very high levels industrially. And not everything is monometallic carbides. It's worth noting things like vanadium carbides come in a wide variety of forms. Not all of these necessarily are commercially useful, but they are technically important because they'll sometimes show up even when you don't necessarily want them present in your product. And then nitrides are the other main category. Boron nitride, silicon nitride are probably two of the most common, also titanium and aluminum nitrides. And then I said there were some other types. Borides, again, are another fairly common class, probably not as common as some of the other materials I've shown here, but aluminum, titanium, silicon, again, just like they form nitrides and carbides, they also will form borides, which are ceramic materials. And then it's worth mentioning that some ceramics, such as silicon, aluminum oxynitrates, they actually do not fall under any one of these categories, but they're a combination of oxide and nitride together. So some of the uses of technical ceramics, abrasives, advanced abrasives and cutting tools are probably one of the main applications, including polishing compounds. Refractories, another very common application, not only laboratory type applications, but industrial kiln furniture, for example, insulation, rocket nozzles, and engine parts. Also structural mechanical parts such as turbine blades, high performance bearings, body armor, different types of composites and protective coatings. And then electronic and magnetic applications, including capacitors, is probably one of the earliest uses for ceramic materials, but also now in sensors, advanced LEDs, and of course, superconductors. And then there's a wide variety of other applications for ceramics in a wide range of markets all around the world. Catalyst absorbents, optics, lubricants, biomedical implants, and of course fillers for polymers and other composites. So another way to look at ceramic materials is not just based on their composition, be it them an oxide or a carbide or a nitride, but also their crystallinity. And that's where you can start to sort of make some clarity. These are all technically ceramic materials in many ways, but they're oftentimes categorized differently. Minerals is one of those categories. They're generally mixtures of amorphous and or polycrystalline, multiple crystalline shapes of a certain compound show up in the minerals. And again, silicates are by far the most common on Earth, but there's also a wide variety of non-silicate-based oxides and silicon materials that technically would fall under a category of a ceramic. Glasses, of course, are amorphous by definition. But these include things like boron sodium, aluminate silica, which is a glass, calcium silicates, so soda glass, and other glass materials. And then technical ceramics, generally we're talking about crystalline materials, although as Akhilesh will point out later, it's also important to understand the amorphous content in these materials. Oftentimes it's a combination of amorphous and crystalline materials, but when we are looking at the ceramic portion, it's generally a crystalline material that we're characterizing. And again, the common ceramics there are oxides, carbides, and nitrides with some examples I show. So what do these crystal phases mean that we've kind of alluded to? I'll give one example here. Alumina is a kind of a classic example to show a material, an oxide material that passes through different phases as a function of temperature in this case. So boehmite is one of the precursors for a lot of aluminum oxide materials. It's a mineral, but it's also obtained from other types of aluminum minerals. And it exists actually in a crystalline form. And it's actually orthorhombic up to about 300 degrees Celsius. Then as you start to heat that material, it becomes amorphous above that 300 degree Celsius threshold. And then once you get to about 500 degrees Celsius, it starts to crystallize again. First, you form a gamma phase, which is cubic. Then at higher temperatures, you will form a delta phase, which is tetragonal. And then at even higher temperatures, up to about 900 C, you'll start to form the monoclinic theta phase. And these are what are referred to as transition aluminas or activated aluminas, because they tend to have active surface behaviors. And also they are a transitional form to the final crystallized form, which is alpha alumina, which is a hexagonal and fully crystalline material that forms about 950 C. By the time you get to 1000 C, you're starting to talk about a pure alumina for the most part. So why does it matter, these different forms? Here are a couple common properties of these ceramic materials as a function, again, of their phase and the temperature at which they were formed. You can see surface area of these materials, fairly stable, around 300 square meters per gram, until you begin to crystallize out, and then they gradually decrease almost linearly until you reach alpha alumina, which oftentimes will have a surface area of about 1 square meter per gram. And at the same time, you see pore volume. Initially, not a lot of porosity. It increases then through the transitional phases before dropping off at the densified state in aluminum oxide. So how do we detect these phases? Akhilesh is going to go into this in much more detail later, but this is an example with XRD. Here you see the boehmite precursor material at the bottom at 250 Celsius. It's fairly crystalline, distinct peaks. Then increasing in temperature, about 300 C, this dehydration occurs and you now form an amorphous material, which is, you can see a very noisy spectra there. And then starting at 700 degrees and continuing up to about 1000, you start to see these semi-crystalline forms of alumina that become more and more clear as the crystals fully form. And then ultimately leading to alpha alumina at temperatures over about 1000 degrees. And you can see very distinct peaks there indicating different portions of the crystal structure. Here's an application of why these phases might be important. Another common technical ceramic is zirconia. At room temperature, it actually exists in this monoclinic state with temperature or a density of about 5.8. And as you increase the temperature, it will transition to this tetragonal phase, which is quite a bit more dense, about 6.1 grams per cc. But what's interesting there is this is actually a reversible phase transformation. So as the material cools off, it will transition back to the monoclinic form. And you can imagine making a product under a certain temperature, and then as it cools, you'd see changes in the structure that would really lead to degradation, cracking, and things that you don't want to happen. And then tetragonal phase, heated even further, will form a cubic phase, which is also a very dense material and stable at higher temperatures, but then once again, we'll revert back to the tetragonal phase at lower temperatures. So there can be a problem anytime you're using this type of material in a application like a rocket nozzle where the temperature changes pretty dramatically during use. These things would crack and break apart if they were changing phase during operation. So it turns out that tetragonal phase and that cubic phase can both be stabilized by adding some chemical modifiers. Yttria is a common one. Here is a crystal structure shown where yttria fills in basically for one of the oxygen atoms at one point. And you can see this stabilized structure. It turns out that cubic structure is actually stable now down to about 1200 degrees Celsius, which is a lot wider range compared to 2300 Celsius. So, and that's a good application. Tetragonal stabilized zirconia is probably actually more commonly used in a lot of markets and applications, but it's interesting to note that the cubic phase is also stabilized. So again, some examples of different phases of these oxide materials, silica and alumina. I've shown you and talked a little bit about the alumina phases. Silica also exists as two different types of phases, a quartz phase and a cristobalite phase. You can see some example properties. There's a lot of other properties that could be shown, but their densities and refractive indexes are quite a bit different. And these and other properties lead to their different uses. So whereas quartz is used in crucibles and electronics, the cristobalite form is used in high performance refractories and coatings. I've already talked about alumina. There's a couple of nitrides, silicon nitride, very common, boron nitride, also very common, but you see they exist in 3 different crystallite forms with different properties. Silicon nitride, you can see the coefficient of thermal expansion there is very low for alpha silicon nitride, and that's why it's used for high temperature engine parts and bearings. And then looking at boron nitride, you see some materials with very high hardness values. Cubic boron nitride, actually, that's more hard than diamond, I believe. So you see its applications in cutting tools and abrasives, whereas hexagonal boron nitride actually behaves differently according to the orientation of the crystal. So it's used in different areas like lubricants and cosmetics. And then I mentioned the silicon aluminum oxynitrides. Here, in this case, the different forms, crystalline forms of this material are the result of different chemical structures. So unlike these other materials that have identical chemical structures, these different phases have different chemical structures. So again, they lead to a wide variety of different applications, from petrochemical equipment to refractories and cutting tools. Carbides are an interesting group to look at for this type of what they call polymorphism, where they exist in these different phases. You see the monometallic examples here of tungsten nitride, vanadium carbide, and molybdenum carbide. So these are 1-to-1 carbon metal ratios and these different cubic or different crystalline forms. And then you see also these bimetallics, where you'll have 2 of the metallic elements in combination with a carbide, but again, some different crystal structures and therefore different applications. Well, they also form in intermediate structures. So you look at vanadium carbide, for example, and you can see 2 more additional carbides. There's many more than this, actually, but 2 more fairly common ones that will show up oftentimes in applications where vanadium and carbon come in contact, such as in alloys and metals. So the way you would distinguish between those different groups would be chemical analysis, simply from looking at atomic ratios. But that would not tell you anything about the crystal structure of each of those. For that, you would have to use a structural analysis tool such as XRD. So that is my tie-in. I'll talk about XRF before Akhilesh takes over and talks about XRD. For ceramic chemical analysis, some typical options shown here where you're looking at either bulk levels or trace levels. You can employ techniques, conventional gravimetric wet chemical techniques. ICP is a very common technique. Go to trace elements, you might use ICP mass spec or AA or DC arc. XRF, you actually have 2 options also. You can do bulk and trace with those to a certain degree. You may, in this case, prepare the samples differently through fusion or pressing, which I'll talk about later. You'll also have to apply different types of standards and software models to use those 2 applications, and I'll discuss both of those. Briefly, the way X-ray fluorescence works is a sample is irradiated with X-rays, and the atoms in the sample hopefully will absorb a certain number of those X-rays. This leads to ionization. So you see an electron shooting off there. That atom is now ionized. And after the electron escapes, it leaves a hole behind in its K-band. And here you see a couple examples where L or M shell electrons are backfilling from higher energy orbitals. So that change, when you have electron shift orbits like that, always leads to an emission of some sort. For XRF, we look at the emission of photons, and both alpha and beta types are shown here for these K-shell electrons, and the spectra that results is going to be characteristic of a particular element. Here's an example of 2 XRF spectra. The top one is an energy dispersive XRF spectra. The bottom one is a wavelength dispersive XRF spectra. And again, you can see multiple peaks for each element Each of the peaks are going to be corresponding to a different type of electron transition. And while the primary, for example, alpha peaks, K alpha peaks oftentimes be the largest area and peak height, you still need those secondary and tertiary peaks in order to do appropriate identification of elements, to do that elemental fingerprint, as is the case with many types of spectroscopy. So I indicated the two types, energy dispersive and wavelength dispersive. Generally, what's applied here is wavelength dispersive, especially when looking at trace materials. It's a higher resolution technique. There's less peak overlap, and those two characteristics lead to generally lower detection limits. One of the issues with XRF is sample matrix effects. Those come from two sources. One is the secondary X-ray emissions. So normally you want those X-rays to lead to the photon emissions, the fluorescent photon emission, which is what we want to do. But sometimes they actually form secondary X-ray emissions. So that requires the use of reference materials to look at the type of matrix effect, and also employment of software models that will probe databases. There's also these macroscopic properties of the sample, such as particle size and shape. And that is why oftentimes different types of sample preparations will be used and optimized for XRF. You can do XRF on solid specimens. This is commonly done for metals. Of course, it requires a smooth and flat surface. Powders can be done in different forms. This is what's often used for ceramic materials as well as many other materials. They can be done in a loose state. It has to be very finely ground so that you get a fairly dense loose powder, and then have to be supported in some type of specimen holder. This generally doesn't work well for ceramics, though. Oftentimes what is used is a press of some sort. So in this case, the powder is pressed into kind of a little pellet along with a binder. This does require the use of milled powder that's fairly fine, less than 75 microns at least. It should be also milled uniformly, and the shapes of the crystallites formed should be pretty uniform. And then you're still going to have to do calibrations with comparably shaped and milled materials. Even better is to use a fused sample prep. Here you form fused beads by combining the ceramic powder with a tetraborate material, such as a lithium tetraborate at about 1,000 degrees to form this fusion. This eliminates the particle size effects and any effects of homogeneity within the powder. The one key is this process does have to be done reproducibly between samples and your standards. And for that reason, fusion of this type is oftentimes done in automated fluxers like the one we have shown here to the right. This is a nice graph I got off LGC's website that shows that generally you get what you put into things. The more effort and cost you put in to do these types of sample preparations, generally the higher quality of the results in terms of resolution and lower detection limits. I will note, though, that both this graph is kind of looking at things from a manual standpoint. So when you look at things like automated fluxers, like the SPEX instrument we have for fused beads, it does reduce the effort substantially. So for some of these, if you introduce a certain amount of automation, besides giving you more consistent results, it can also reduce the amount of effort substantially. So then I also mentioned, aside from sample prep, calibrations are important, and you have to have some sort of software and calibration system in place to do this. We use a software package and CRM package called Roxy for major and minor species. This is a package that's comprised of 17 fused bead CRMs that represent 21 oxides over the ranges shown here. Then for trace analysis, we use a product called ProTrace. It can be used in two different ways, either along with matrix matched reference materials. Of course, these are limited in terms of availability for a particular composition. So oftentimes, one will have to resort to a non-matrix matched reference materials. For this, the package of ProTrace can include some blank specimens as well as what they call setup samples. These setup samples have been validated against CRMs, and they consist of 25 pressed powder standards and blanks that cover about 40 or more elements. Here's quickly some results of FRX using ROXY. Here, this first sample was done using a soda feldspar reference material, and you can see it's mostly alumina and silica with some soda in it. If you look at common aluminosilicates, that's pretty high level of alumina. So it would suggest that this is either a molite, the calcine material to form molite phase, or potentially a bauxitic clay, which does contain a significant amount of silica as a clay would, but these larger amounts of aluminum also. And then another example here used a Sierra reference material that was a zircon, so it was a zirconium silicate. And again, you see some hafnium there at about percent level. That will always occur naturally when you have zirconium materials simply from natural abundance. But then you see some other minor elements there, alumina and titanium, yttria, also fairly common oxide materials. And so by looking at this, it looks like this material is about a 98% pure zircon product that was probably made for a refractory application or abrasive. Okay, with that, I'll hand the mic over to Akhilesh, and he'll talk to you about XRD.
Thank you, Dave. I must say that was very knowledge-enhancing talk for myself, also in this field. So again, I thank you for that. So everybody, we shift gear now to XRD analysis, particularly in light of ceramic materials. You all saw that ceramic materials have a very wide range, almost covering a big area, big chunk of inorganic materials. So that helps. These materials are generally very crystalline. So quickly, Rigaku Analytical Technologies, where do we land in this? As I mentioned briefly in the first two slides in the beginning of this talk. So XRD, for example, the X-ray diffraction provides crystal structure, lattice constant, and a number of information that we will talk about for these ceramic and related materials, and nanocarbon, nanoglass, battery materials, superconductors, nanometals, just to name a few. Actually, there's a lot of them. But for ceramics, another area which we can see these ceramics, as we learned, could also be in electronics. So XRD has another area, which is thin film area. So the ceramics could be in the form of thin films on a substrate, and these can be analyzed very well, again, by thin film analysis. And then you have other things such as SAX and XRR for thin film analysis and SAX for particle size analysis. And then we have other areas, XRT, TA, and Raman. But let's see today in this talk a little detailed study of XRD. So I decided to divide this talk into 5 parts. What all can you do with XRD? A little bit basics of XRD. A sample preparation, though very simple, but we will talk about what one should not do and what one should do for the sample. A little bit insight into the instrumentation, application, and finally of a slide or two for X-ray safety in light of all these instruments. So why X-rays? I thought about this also when I was young. Why can't we have a very high powerful microscope to look into very small features in materials? But realize when we want to look into materials, our limiting factor is the wavelength with which we are looking. You are looking at these slides because the light is falling on that, which has comparable wavelengths, and you are receiving this reflected light in your eyes, and you're seeing all this. But if we want to see something at atomic level, we need a comparable wavelength. And X-rays are the only part of the wavelength that is providing this sort of wavelength, where we are looking at atomic lengths, atomic bond lengths, and hence we can study the crystal structure, which are very much related, what we learned from Dave's lecture, to the properties of the material. So crystal structure and property are related. Let's look this in light of Bragg's law. So every material in this world, especially all the crystalline material, can be considered as consisting of layers of atoms, layers of atoms in some relation with each other. Okay, so this theory is very different than the XRF one. So when we shine XRD on it or X-ray on it, what happens is it is diffracted, not reflected. It's following a law of diffraction. And we are paying homage to Dr. Bragg and his son. Both got Nobel Prize, actually, for enhancing this work, father-son duo. And so this is diffracted, but But if you can imagine this, several layers can either enhance or this X-ray, which has wave-like character. So you can have constructive or destructive interference. That's the word. Depending on how far these layers are and which atoms compose these layers, as this X-ray, in terms of several wavelengths, hit the material, we are having constantly constructive and destructive interference. So imagine your instrument is providing the X-ray, hitting the material, and based on your material, which is unique in the sense that they have different d spacings and the atoms, you are getting peaks at different positions. So everybody understand this is how the peaks are coming. And this difference in wavelength, if you see the grade, the difference in length between the two waves is when it satisfies Bragg law, you have a condition fulfilling for the phenomena of seeing a peak from Bragg's law. So hopefully next 2-3 slides, it will be more clear. And then we should talk about these planes, because remember I said these planes are what is causing the X-ray to either be in constructive or destructive interference. So we call them Miller indices or HKL planes. When these planes satisfies Bragg law, you have a phenomena of seeing a peak. So let's see. Yes, so that's how a diffraction pattern looks like. You have intensity on the Y scale, you have a 2 theta, which is how your diffractometer is moving. And wherever these planes are causing constructive interference, you are seeing a peak. And that's why sometimes you can see on the top of the peak, it's written 1, 1, 1. This is the 1, 1, 1 HKL plane, or 2, 2, 0. These are the 3 ABC direction in which the atoms have lined up properly to cause this diffraction phenomenon. So then in the third cartoon, you see powder or polycrystalline material. So when we make something powder, we have this plane in all possible orientation, and that can satisfy Bragg law. So we will see all the peaks for that particular material that are possible, which are having a constructive interference in Bragg's law. So those are the most ideal material to do diffraction. However, if you bring a single crystal, something like, let's say you have a piece of diamond in your jewelry, it has to have the right orientation to satisfy Bragg law, because you are trying to see just one of that plane. And that's why you have to keep rotating it, or either automatically or by your manually to see a peak. So that's what is called single crystal. And then there is another way to find the structure. So the second cartoon shows a liquid or amorphous. That's where the lattice structure, the sort of repeatability that is present in crystalline material is missing. And hence you see something we call as amorphous hump. It has a lot of information, and it is utilized in XRD in several ways that we will see. But however, the information is a lot lesser in terms of having a database for amorphous material. There is no such database. Gases, the atoms are very far apart, and essentially XRD provide little or no information about the gases. So next, let's talk about sample prep. Quite straightforward for most of the materials, ceramics in general. You make a fine powder, and as number 1 point shows, you took an appropriate amount, and there is always a well or a place in the sample holders where you can fill in, and then you can use a microscope slide or any other slide to pack it, press it, and in point 4, you see it's well packed within the groove or well of the sample holder, and it's neither above nor below. We will see that in some slides. It is very important. The samples should be packed and presented this way to the diffractometer for collecting a very nice data on the sample. All samples do not present such an easy scenario of grinding them. So usually, like here, a agate mortar or most mortar and pestle is enough to grind a sample into a size roughly 20 to 80 micron or 325 mesh. However, in some cases, electrical milling machines could be utilized to achieve such a size. It's fairly common to use such milling machines. So then you could have a couple of scenarios. We talked about fine powders, which can be put into these sample holders, as you see here. If you have less sample, there are zero background or low background sample holders, usually a silicon cut in a direction that has no peak in X-ray diffraction. So where you can utilize minimal amount of sample. Still, there are situations. There is a sort of ceramic block shown in the picture too, where you can see it could go on a bulk sample holder. So these bulk sample holders will analyze the top 100 up to 100 nanometers of the sample where X-ray reach and can give you a fair bit of idea. And then there are other types of sample holders shown in third picture, which could be of the type of some liquid, like viscous liquid with with particles in it, or a transmission geometry. So depending on the situation in each cases, whether it's a grounded sample or a bulk or a liquid, different sample holders do exist. So let's take home point from the sample preparation is for X-ray diffraction purpose, we need a well-grounded particle. If you are doing it with mortar pestle, you shouldn't be hearing any crackling sound as if you were starting with sand, but then you smoothened it out. So in terms of actual size you hit, when you don't hear any crackling sound, it's roughly 325 mesh or 45 micron. There were some people do use sieve, but you can yourself feel if the particle is smooth because it becomes spherical and you do not have any this crackling feeling. Sample could also be loaded in, as I mentioned, if they're in less amount, in zero background holders. And there are sample holders for plates, thin films, bulks. They exist for analyzing the top parts of the sample holder. So then you are ready with your sample, whichever type, powder, bulk, or even liquid, and then you have to put them on the instrument. I'm showing here in the three pictures, two of them are on the Miniflex with a single sample holder and a 8 ASC, we call it, auto sampler chain 8. And in the middle, there is a smart lab. So most of the instrument, the optics idea is very clear. You have an X-ray generator, which could be a rotating anode or a seal tube type, which produces this X-ray. It passes through a number of optics. Usually we call them incident optics, consisting of divergence slit and Solar slits. Or it could provide you a Bragg-Brentano or parallel beam type geometry. And then you have a sample in the center, which we call goniometer. You could put multiple samples, thin film samples, which are shown on both sides of this middle picture. You have different samples, zero background holder containing very small amount of sample. And then you have a diffracted side where the main component is detector trying to receive this diffracted X-ray coming out of the sample, which we call as the peak. And it passes through several receiving optics, basically making sure the signal is converged onto the detector. There is attenuator and a number of receiving slits. So we prepared the sample, we collected the data, and this is what, in general, if I make a cartoon of a diffraction pattern, it would look like. You could have this big hump mixed with crystalline peaks. So big hump is coming from the amorphous material, the amorphous part of this material, and crystalline peaks are the crystalline phase of the material. So let's understand a few terms here. If we take the ratio of integrated intensity in the crystalline peak and in the amorphous peak, we can get the idea of what is the percent crystallinity of this material. This is quite important these days, not that we are always looking for 100% crystalline material. Properties of the material do change when there is an amorphous mixture in them. So these are considered very important. The widths of the peak shown right here in the red peak, right in the middle, are very indicative of the crystallite size and strain. For example, if you have nanomaterial, this width of the peak would be very broad compared to a crystalline material. So when the nano word came, you could quickly put this material and see they had very broad peaks. So peak position is very indicative of lattice parameter, which means how much this material differs from other known material of similar type. The whole pattern as such will give information on the phase identification and quantitative analysis. So we have collected data. So let's see few applications that XRD will provide. The most widely acceptable and used application is phase identification. What is this material? So there's a list of completely exhaustive databases, especially for inorganic ceramic type material, which will immediately tell you what material it is, and so that you're aware, or even a mixture of several phases. In cement analysis that I have done, usually they're a mixture of 10 to 12 phases, and you can precisely tell each one of them and in how much quantitative amount. So we'll look into this word precisely is how precise. Secondly, you can tell crystal structure analysis. If you are modifying the material by some atomic substitution, you can tell how much atomic substitution was achieved or which you were desiring. And quantitative analysis will tell you how much each material is present in quantitative. Now, quantitative analysis by XRD can go up to 1% if you are using calibration type of approach, or they could have error up to 3% easily when you're using whole pattern fitting type of approaches. So just to make sure we don't look here into parts per million type of accuracy, we look into some percentage, up to 1% by using calibration methods. Percent crystallinity can tell you, as I mentioned, how much of your material is crystalline and how much is amorphous. Crystallite size and lattice strain are very important to see how properties of the material have changed. For example, when they were modified into a different material. When you create a wing of an aeroplane, you have strained the material, and lattice strain can be calculated on, let's say the material was aluminum. So, and similarly, lattice parameter refinement tells you a lot about any change in the lattice, the smallest building block of these materials. So once you actually collect the data, there are, if I could broadly divide the three parts, you can identify the material using a database. These databases are, like I said, are pretty exhaustive. I listed here ICDD, International Center for Diffraction Data, an independent body that sells these databases containing the list of almost the full list of all the materials, their diffraction pattern that can be matched. The diffraction angle, intensity, and width are indicative respectively of lattice parameter, quantitative analysis, and crystallite size and lattice distortion. In the most advanced part, one can do reed-weld analysis or whole pattern powder fitting. Herein, people are studying in depth if they are doing atomic substitution. That is, I will bring in one example to elucidate this point, that if you are changing an existing element with other element to change the properties. Like I mentioned before, crystal structure and property are two sides of a pan. If you change one, the other side has to change to reflect the consequent change in the property. You can do other techniques too. So phase ID, quite straightforward these days, as long as you don't have 15 or 20 phases, pretty straightforward. I'll try to show that in an example today. So this is a mixture of zinc oxide, magnesium oxide, and alumina. Could put it in the case of ceramic type material, as Dave mentioned. So you could collect the data, do a reed-weld analysis, which makes actually a model based on the phases you tell. And this model actually completely masks the actual pattern. And this is called refinement. You can a little bit refine this model until it masks the actual data. And once the masking of the data is complete, which is shown by those two little numbers there, are R and E. R is the residual parameter, and E is the goodness of fit. And once this is very good, which is also shown by a green line at the top, which is called the difference pattern, which is left nothing, means my masking is very good. My model or my calculated pattern is very close to the actual data. And then we have all information about this mixture of phases. In this case, we are saying corundum is 36%, zinc oxide 20%, and magnesium oxide 44%. As I mentioned in the beginning, it is not limited only to powder. Here I'm showing two cement blocks, which for some reason I was told in this project that let's not try to grind them into fine powder, which is the ideal situation, but we can still analyze them and get a fair bit of idea of the phases present in this scenario. Although, like I said, this will tell the top information from the top parts. And in this case, one can easily see these are cement phases, which is a ceramic material, hardurite, anhydrite, larnite, brown millerite, gypsum, and lime. These names are used by people in cement industry, but these are calcium oxide or calcium sulfate type of compounds. This is an example just to show one of the things that I said, how close do we get with the actual composition of the material? This is a NIST certified material. Most of us are aware, National Institute of Standard and Technology, they preserve, or they have the materials as standard reference material. This is a standard reference cement standard. The certified values are given in mass percent in the last column. And using a read build method, you can see the phase compositions are very close to the certified values. So this is how close one can get. Look at the 5th column, arcanate potassium sulfate. So here, that's some sort of difference you can expect. But this is, in our language, a minor or a trace phase, and easily these type of differences are visible from the actual to the real. Let's turn attention to one more thing. XRD can provide unique in-depth information. This is a crystalline silicate titanate material on the left, and a 25% substituted crystalline silicate titanate material on the right. So what happens in this material on the left, there are titanium octahedra connected to silicon tetrahedra. And this material, CST, is a well-known material. It is known to our national labs. It can, a radioactive cesium can get stuck in this kind of materials, sort of entrapped. And then this can be further vitrified and can be saved in caves. There's a whole project on this line. But it was found that this material actually is stuck much better in a niobium substituted crystalline silicon titanate. So this project came to us to see why that happens, that once you have a niobium substitution into the material, cesium is more stuck and does not come out of this material. And again, by Rietveld refinement in XRD, an XRD technique, one could find that once you substitute some of the titanium octahedra by niobium octahedra, the tunnel in which the cesium goes gets slightly larger, allows the penetration of 4 water molecule that gets stuck to cesium. And now cesium is bonded to 12 atoms compared to the 8 atoms on the left side. And this is what causes this material to get stuck much better. So this is all can be achieved from the Rietveld analysis technique. Changing topic to how much material do we need if we are in a situation we don't have much material. Practically these days, I've gone to some conferences, we have talked. If you can see a material, you can get an XRD pattern. This is how everyone says with the enhanced, improved optics and the new high-speed detectors. This is just a 0.05 milligram powder on a 0 background holder. You can see in this picture. This is a API material, carbon, hydrogen, nitrogen, pharmaceutical material, and even those materials which do not have high atomic numbers, both the API and lactose hydrate can both be seen in a 3-minute scan. Dave talked about some conversion of bohemite to finally corundum form. So yes, these kind of studies are known as in situ studies. They can go, you can take the material to the type of attachment you have, high temperature attachment, such as this one is shown as a 1500 HT, high temperature 1500 attachment. This attachment is actually 500 attachment, which is shown in the picture, but this data was collected on another Rigaku high temperature attachment called as HT 1500. So in these in situ measurements, there is a third dimension of 2 theta intensity and time and temperature. So you can heat the material and collect the data at a desired temperatures where you believe either the unit cell is transforming or the space group is changing, where that's why they mentioned orthorhombic to tetragonal to cubic forms, and these phase changes are easily visible, and you can notice the behavior of the material at specific temperatures. Some samples are air sensitive samples. They can either in the presence of moisture, they can go to their hydrated form, the hydroxyl OH form, or the H2O form. So these materials need to be studied in special air sensitive sample holders, which can be prepared in a glove box. You can see in this 2 diffractograms, we are showing the behavior of iron chloride. If you're doing it simply without these special sample holders, air sensitive sample holders, the material can decay in a short period of time, as shown with the third blue pattern, which is totally amorphous. But in a air sensitive sample holders, the material will retain itself and would not react with atmospheric oxygen or moisture or anything that you're trying to avoid its interaction with. So we talked about, in short today, the 3 key features some basic idea why do we see peaks, and then how to prepare a sample to the level of collecting data and what are different applications. But of course, when it comes to X-ray, everybody has some sort of worry about everything is safe. I've heard the question sometimes, people thinking these X-rays are coming from some sort of a uranium containing a material. The X-rays are produced in a sealed tube, which have which there is a potential difference between anode and cathode, and a current is flown to generate the X-rays, and they are very well contained in these instruments. They are foolproof safety features as shown in this, wherein these interlocks will simply put the shutter, which will put the shutter in the engaged position, so that you cannot have forward going X-rays when the doors are open. So all the doors as shown in this picture also goes into these door interlocks, wherein as soon as you open the door of these equipments, there could not be any production of X-rays in the forward going direction. So just a few pointers again, away from this talk, just like what is a batch sample preparation? When you have well-packed smooth surface right into the well of the sample, you get a nice diffraction data, peaks are not shifted. When you have sample just put on the sample holder without any preparation, without any packing, you can get, this is same sample exactly, but you can get not only shifted peaks, but a lot of noise. We call it poor signal to noise or bad peak to background. Both terms are very, very well known. And there are shadow effects, there are displacement effects, both come into picture when samples are put in this fashion. Again, in light of current last 2 years of COVID situation, I just wanted to mention, I understand, unlike IT people, we can't do everything from home. So there are situations we have to be in the lab to put the sample, but 48 to 120 sample changers exist in these equipments, where you can load them with that many samples and remotely control these equipments so that you can then analyze the data with the software once these are collected. And last but not the least, Miniflex is our state-of-the-art benchtop X-ray equipment. We started world's first benchtop equipment in 1973, calling it now as the first generation. It saw many stages. 1995, world's first benchtop operated by Windows. 2005, world first benchtop loaded with 1D detector, which actually enhanced the speed 30 to 40 times of the conventional 0D scintillation counter detectors. And then we came up in 2010 a 600 watt, and it used to be 450 watt instrument. And we call that 5th generation, but now we even have 2D detectors, 600 watt, 6th generation Miniflex 6G.
Okay, thanks, Akhilesh. Stay on the line here. We'll have some questions and hopefully answers here in a minute. But just to wrap things up, I hope we've shown that technical ceramic materials include a really huge range of types and compositions and crystal structures, and these differences in types and this huge range account for their wide use in different markets and applications due to their unique properties. And as Akhilesh has mentioned, these properties are very strongly related to their crystallinity as well as their composition. X-ray fluorescence provides you with good bulk and, in some cases, trace elemental composition. It does require careful sample preparation and calibration.
Yes, so continuing with what Dave mentioned, X-ray diffraction is virtually the only technique capable of probing an array of crystalline structure in semi-crystalline or fully crystalline ceramics. And I hope I tried to put forward that XRD is a very viable technique that provides an insight into a wide variety of materials, both crystalline and amorphous. Structural insights, which we saw today into materials, is critical to their understanding and fine-tuning the existing properties.
All right, with that, I'll turn it over to you, Melissa, if there's any questions that have come in.
Absolutely, very good. Thank you, gentlemen. One of the first questions, Can XRF and XRD data be combined together?
Dave, I will answer this, and you can add things. Yes, I'll show in software also. Yes, XRF provides elemental analysis, and elemental analysis are actually read can be easily read into our softwares to find the compounds. I call them like sort of brother sister, because when you are looking for trace or minor phases, element information becomes very critical to find the compounds. Dave, you want to add something to this?
Yeah, I've never seen an actual instrument where it was combined, but going into XRD, having that XRF or some other chemical information is a huge head start into identifying, matching up to the proper pattern. So you almost need to have both of those sets of data together.
Very good, thank you. Does the software ceramic search option work for all the databases or just the ICDD database?
Melissa, can you repeat that question? I thought that was for ceramics.
Yes, I'm sorry. For XRD, does the software ceramic search option work with all databases or just the ICDD database?
Yeah, that's a very good question. So actually, allow me to just quickly show the software because I can't answer this without it. So let me share my screen for answering this question. So Melissa, can you see the screen I'm showing?
Yes, I can.
Okay, so I would load a data quickly, guys, to show all of you this part. So depending on the database, yes, you can divide it into only searching ceramics, and some database won't do it. It's better to just quickly see this in. So this is our Smart Lab Studio software, kind of very easy to operate, flow-like chart. You just read the data, automatic peak evaluation. Then I'm right here on phase identification. So then I hit here search match, and that's where the answer is hidden. So in the search match, you can see specify subfiles. I can divide it into just looking ceramics. Here you can see, but not all the database. There is a lot of database I have. All ICDD database are dividable into ceramic, but databases such as COD, which is a free database, it's a free database. You can't even guarantee everything is there or not, but it's quite huge, and it has grown huge over a period of time and doesn't have this facility. It has not been divided into subfiles. And also ICSD, Inorganic Crystal Structure Database, a FIS-NIST product, is also not divided into ceramics. Later on, I might show a little bit more of this features of this software, but at this point, just answering this question.
Does this database have a yearly license?
So there are different databases by ICDD. The PDF2 database has the longest license of 5 years. It doesn't have crystal structure information. Their PDF4 Axiom database is 3-year license, but their PDF4 database, for example, yes, it is a yearly license. And these are independent products of Rigaku. You can buy them independently from ICDD, for example.
Okay, thank you. What is the preferred orientation, and how does it affect quantitative analysis?
So we all studied today in the lectures about collecting a pattern such as what is shown here, but some materials tend to have preferred orientation, which could be, for example, fiber-like material or some clays, which are also part of ceramics. Or in these materials, certain peaks are a lot taller than what they should be because the material tend to lie on a certain planes. We understood planes causes peaks, but if the material has a preferential orientation towards certain planes, then those peaks will be taller. In that case, positions are not affected, but quantitative amount of that particular phase is affected because its peaks are artificially taller than what it should be. Corrections exist in the software to let the software know that I have preferred orientation, and one can correct it.
Very good, thank you. And then I see one last one, and if anybody online would like to add something, we can go through a couple more questions too. This question, how do we decide the step size in the data collection?
So I'll answer this, Dave. Usually the peaks should be collected in 5 steps. So if you divide the full width half maximum, which we talked about, which you can see here, by 5, you know the step size. A lot of people tend to think very small step size will give them great data, or some people can accidentally put a very large step size. Both these things could result in not so good data collection. So one should take it in his quickly collected data, the FWHM, smallest number, and divide that by either 5 or 7 to get a fair bit of idea about the step size for data collection.
So I don't see any more questions coming up. Dave or Akhilesh, are there any final things you'd like to share?
Yeah, for the general idea, I want to finish this. If you are still seeing my screen, I just want to finish showing how easy phase identification and a quick read-well refinement would be. May I?
So right now we see the Q&A screen, so you'll have to
Okay.
go again.
Okay. Screen 2. Are you able to see my screen now?
Yes, we can. You're all set.
Okay. So we loaded this data, which is likely a mixture of 3 phases, and we can see how just going through this flow bar, we can find the phases and find their quantitative amount. So we read this data and we asked the program using search match. We could have said, like, for example, it's a ceramic or inorganic, but if we don't know, we can also say all subfiles. Element filter, there was one question related, someone asking, can we use XRF data? Yes, you can load, but Dave correctly got the right part that hardware-wise, the two have never been combined. Software-wise, you can read the data coming from XRF elemental analysis into XRD. So if we don't know the elements, it's okay in this situation. The peaks are quite separated. We can choose a database we discussed. These are the peaks we need to find, and we say run. The software goes into the database, just like I was saying. This is almost like fingerprinting type. We have fingerprints mixed, and we can tell whose fingerprint are these. Annotate's fingerprint, those green lines you can see up and down. I'm just scaling. Rutile here and calcite. So we agree. Once we agree, we can hit the button set. So it's users. The answers always does not come that straightforward. Sometimes you have to bring in some entry. Sometimes you have to decide, no, this is not my phase. But once you think there's all the phases that you were expecting are found, you can pretty much hit set. And then you have the information. Their crystal structures are here, which we talked in general. And then we can save these results. And then we can easily go to the other part of the program. And for example, this is read-well analysis, where we can tell by a quick refinement of this, which means fitting a simulated or model pattern on the actual data. And then we will know how much of these 3 phases are present. Anatase 47, rutile 11, calcite 41. So, and a number of other analyses are apparently clear at this point, such as unit cell, percent crystallinity, and a crystallite size. That's all from my side, Melissa.
Okay, very good. Dave, anything else on your side before I finish up?
No, that's good. I didn't mention it, but we at NSL actually have the Rigaku MiniFlex, so it was very informative for me to hear Akhilesh's discussion. Of course, here's our contact information. Don't hesitate to contact either one of us if you have any questions. We look forward to hearing from you. Melissa, anything to close off on your side?
Yes, thank you. So I'd like to thank everybody for tuning in today. We appreciate this opportunity to share this topic with you. After today's webinar, you'll receive a short survey. Please take a moment to fill out the questions. This will help us improve topics moving forward and in the future. Thank you, everybody. Have a good afternoon.
Thanks.
Thank you, everybody.